scientific death.
On January 15, 1919, a massive structural rupture in Boston created one of the most lethal industrial accidents in American history. The Boston Molasses Flood is now a cornerstone case study in fluid kinetics and structural failure. When the Purity Distilling Company tank failed, it released 2.3 million gallons of molasses. At 1.4 times the density of water, this payload generated a kinetic wave that stood 40 feet high and moved through the city streets at 35 miles per hour. The mangled wreckage under this railway is the result of a complex thermodynamic cascade. Internal pneumatic pressure, triggered by rapid gas generation, completely overwhelms the structural limits of the vessel's riveted seams. To understand exactly how this rupture occurred, we must deconstruct the static loads, isolate the sudden thermodynamic catalyst, and examine the resulting fluid dynamics. Finally, we will look at the specific engineering legislation this disaster forced into existence. Evaluating the precise mechanical intersection of these variables explains why modern engineering strictly requires independent certification and the rigid calculation of safety factors for all major industrial structures. This diagram outlines the Purity Distilling Tank, 50 feet tall and 90 feet wide. The fluid's outward push represents baseline hydrostatic pressure. Because pressure scales linearly with depth, the fluid at the bottom exerts maximum outward force on the lowest structural rings. The tank was structurally compromised from day one. Its lower steel plates were mathematically too thin to contain the molasses. Furthermore, riveted lap seams forced the internal outward pressure to concentrate into tiny, highly localized stress points. Engineers refer to this constant outward radial force acting against the walls of a cylindrical vessel as hoop stress. Even under static conditions, the immense density of the liquid pushing against thin steel and localized rivet points meant the structure was already operating at the limit of its hoop stress capacity. The breaking point arrived via an external environmental variable. In the days leading up to January 15th, Boston experienced a rapid ambient weather shift, jumping from -11 degrees Celsius up to a warm 8 degrees. Around this same time, the facility pumped a fresh, warm batch of molasses into the bottom of the already full, heavily pressurized tank. Warm temperatures initiated localized organic fermentation within the molasses. This generated massive volumes of trapped carbon dioxide gas. The expanding CO2 created new pressure vectors against the roof, adding extreme, uncalculated dynamic force that completely exceeded the structural limits of the riveted joints. Rupture became inevitable. A marginally engineered closed system, lacking the safety margins to absorb thermal expansion and gas generation, simply could not hold. At 12:40 p.m., the combined hydrostatic and pneumatic loads finally surpassed the critical shear strength of the metal. The iron rivets sheared off with sounds like machine gun fire, and the tank's structural seams completely unzipped. The immediate displacement of that dense fluid generated an initial kinetic wave, moving at 35 miles per hour, acting as a massive wall of blunt force. The momentum of this dense liquid was high enough to demolish buildings and flatten an adjacent elevated railway structure instantly. But the impact was only the first phase of the disaster. Molasses is a non-Newtonian fluid. Unlike water, its viscosity actively changes based on the surrounding temperature and the physical force applied to it. As the wave spread, it lost its forward momentum and cooled in the winter air. This caused the fluid's viscosity to increase dramatically, turning it into a thick, inescapable sludge. For anyone caught in the flood, the fluid acted like quicksand. The harder victims thrashed to escape, the more shear stress they applied, causing the dense liquid to trap their limbs more securely. This immobilization led to mechanical asphyxiation. The extreme weight of the dense fluid made it impossible for their thoracic muscles to expand, causing rapid suffocation. The unique lethality of this event was driven by the molasses acting in two distinct phases, first as a high-momentum kinetic weapon, and then as a high-viscosity mechanical trap. This aerial view shows the total flattening of the local industrial sector, where buildings were demolished and iron infrastructure was twisted. 21 people died because industrial blueprints were unregulated and uncertified. Landmark lawsuits following the disaster forced a permanent legislative correction. The state of Massachusetts instituted a legal mandate that all structural blueprints for major public and industrial works must be explicitly approved by a certified licensed professional engineer. The disaster also led to the standardization of rigorous factor of safety calculations for all pressure vessels and storage tanks. Today, tanks are engineered to withstand 3 to 4 times their maximum expected hydrostatic load. This ensures they can absorb unaccounted thermal expansions or internal gas buildups without breaching their structural boundaries. Forensic study of the sheared rivets also accelerated a massive shift in manufacturing. Construction transitioned away from riveted lap seams and moved toward full penetration arc welding. Welding provides a profound mechanical advantage by fusing metal panels together. It treats joints as a continuous, uniform metal field, eliminating the localized stress points that caused the Boston tank to unzip. The Boston Molasses disaster remains a foundational case study because it transitioned structural engineering from an unregulated industrial practice into a mathematically rigorous scientific discipline.
If you enjoyed this video, please remember to like and subscribe. And don't forget to comment below with your favorite emoji.